Welcome to Chapter 5. Standard error and inference are going to be two of our very important and key concepts in this and carrying us into subsequent chapters. This is the very backbone of statistics. So recall that we have talked about sampling a little bit. We talked about populations and samples from the populations. And last chapter, we introduced probability distributions, and in particular, we talked about the normal distribution, and we talked about the binomial distribution, where things take on one of two values, yes or no. So we've got some foundational concepts here. What we're going to do with them in this chapter is we're going to talk about sampling distributions. Notice distributions comes in again there. We're going to talk about the central limit theorem, and then we're going to start doing inference with proportions, and we're going to do confidence intervals and simple hypothesis tests. So first of all, if we talk about sampling, we could ask, how many samples of a certain size could we take from a larger but finite population of size capital N? Okay, so how many unique samples of size little n could we construct? And this formula should seem familiar because this is basically the front piece of the binomial distribution. And in the binomial, we had it in the form n factorial over x factorial n minus x factorial, where x was the smaller number and n was the larger number. So this is the same formulation, it's just using some different notation because now we're talking about from population to sample. So, for example, suppose you examine 82 graduate statistics programs in the United States and record the number of students enrolled. What if we want to take just a sample of 10 of those? Okay, so how many samples could we construct of size 10 from those 82, right? So we could have schools 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, etc., right? So if we do this formula, we have 82 factorial, that's our population size, 10 factorial, that's our sample size, and then 82 minus 10 factorial, which gives us 72 factorial, okay? And we will learn how to put this into R if you don't have a factorial key on your calculator. Otherwise, you can put it in the calculator, and you can also do some simplification to make these big numbers a little bit more manageable sometimes. But this ultimately comes out to 2,139,280,241,670 samples. That's an awful lot of different options here. What does that look like? Let's go look at a simulation here. Okay, here we are in StatKey, and we are looking at those 82 statistics grad programs. Note that there are a bunch of different data sets here, but we want to look at the stats grad schools. And if we come over here and look at the population, there are indeed 82 schools. This is the enrollment numbers for stats doctoral programs in 2009, I think. And the average was 53.537, the median's 45.5, and the standard deviation is 36.89. And so what if we generate a sample of size 10? Remember we said we could do a lot of those. So let's generate one sample. That sample is size 10, and the mean is 64.6, so not quite what the population mean is. The standard deviation is higher than the standard deviation in the population, and it shows you how the data points are distributed. Okay, let's generate some more samples. Notice that this one got plotted here We generate 10 samples. Now, these are the different samples, and those are their means. So they all have a different sample mean, but the mean of those means is 56.964. If we generate 100 more samples, it does that. If we generate 1,000 samples, and now look what's happening. It's starting to look kind of like a standard normal curve, a z-curve. Notice that in the population, it's not distributed quite that way, but when we take many samples, it starts to resemble that plot. And the more samples we take, so now we have a little over 2,000 samples, right? The more samples we take, the more it converges to a standard normal curve. Okay, so that's the idea of being able to take multiple samples from a population. Why would we want to do this? That's a good question. So we usually take samples to provide some kind of information to help us understand the population. So the samples provide estimates, and we call them point estimates, of population parameters. Okay, so for example, mu is the population mean. The sample point estimate, the statistic, would be x bar. Sigma squared and sigma are the population variance and standard deviation, and the sample variance and standard deviation is s squared and s. And now we're going to have a new one, rho. Some people use pi for this, but I find that that confuses people if I do that. So we're going to use rho, and that is the population proportion, and the sample corresponding statistic is usually denoted p with a bar on it. So x bar for the sample mean, p bar for the sample proportion. The sample statistics are good estimates of the population parameters in that they are unbiased, that is, the expected value of the sample means is mu. They are efficient, which means they give the smallest standard error, and we're going to define standard error soon. And they are consistent, so they become closer to the population value as the sample size becomes larger, and that's very helpful. So here's an example. You have a population that only has 20 observations. Here are the 20 observations, and the mean of these, mu, is 540.5, and the standard deviation is 38.7. If we plot this on a normal curve, remember we can go up and down 1 and 2 and even 3 standard deviations. This is what it would look like. So plus or minus 2 standard deviations goes from 463.1 to 617.9. So what if we want to take a sample from this population? Suppose we want to take a sample of size 5. Okay, so first, we could ask how many possible samples of size 5 are there, and it will turn out in a minute there are quite a lot. And then we can ask, what is the mean of each sample? So we're doing here pretty much what that simulation was doing. So the first sample we take is 520, 550, 490, 530, and 620. The next one we take is 520, 535, 525, 620, 550, etc. By the way, when you figure it out, remember the big N factorial over little n factorial times big N minus little n factorial. You'll find out there are 15,504 possible ways we can take a sample of size 5 from this little population. So for each of these samples, we compute their means. The mean of the first one is 542, the second one's 550, and the third one is 533. And this is what they look like if we think of them as being the center of our normal curve. So here's the population, 540.5, that's the black one. One of the samples gave us a mean down here of 530, so that's this red curve. Another one gave us one that's pretty close to the 540.5. That's the green curve with a mean of 542. And then one gave us one way up here at 550. That's the purple curve. Okay. So if we compare our population and our samples, the population size is 20. The samples were of size 5, and they each had different means. The mean of the population was 540.5. And remember, we said that the expected value of the mean should be the population mean. So if we take these three sample means that we got, the 542, 550, 533, and compute their mean, then we have 541.67, which is close. It's close to the population mean. The standard deviation of the population was 38.7. The standard deviation of the sample means, if we put them into this formula over here, where each x is a mean, so that would be like 542 minus 541.67, and square that. Do that for all three, then divide by 3 minus 1 is 2, because we have three means, and take the square root, you get 850. So this is a standard deviation of the sample means. This is a measure of the variability of the sample means. Not of each sample, not of the population, but of the group of sample means that we generated. And this is an important idea. We can start asking things like, well, okay, if the population mean is 540.5, what is the probability of getting a sample mean of 530 or less, right? And this is starting to think about z-score ideas again. And so remember, z is equal to a value minus a mean over standard deviation, right? So 530 would be a value, and 540.5 would be an overall mean, and then we would need a measure of variability. Now, we just calculated a measure of variability here, right? The standard deviation of the sample means is 8.5. So in this case, we've got that. But do we usually have that? No, because usually we have one sample. We take a sample, and samples are time consuming, they're expensive, they cost money. So we only usually have one sample to work with. So great. Now what are we going to do? That's up next.